Good morning, class. Today we're going to be looking at polymorphism, which literally means many forms and is implemented in a lot of different ways in object-oriented languages. So today we're going to focus on just a couple of those. So we have this example project called Does It Blend, which is inspired by the YouTube channel BlendTech's Will It Blend. If you haven't seen this, it's a great way to waste some time.
That is the
And it's all about blending things you would normally not put in a blender. And it's probably better to watch the channel than try it yourself, because some of the things that they're blending, really it's not a good idea to blend because they contain various materials that are very harmful to your health. So let's go ahead and take a look at what we have. We have, for example, a class representing a banana, and we have a class representing ice cubes. We have a class representing a mango. We have a class representing a strawberry. So all of these have a blend method, and we want to be able to put those together and actually go through and blend those as part of our program. So we're going to start and say, let's add a list. And the question is, what kind of list can hold all of the things that we want to potentially add in order to blend? So for example, if we just created a list of banana, let's call this fruits, new list banana, and we tried putting a banana in, and of course we have to have the system.collections.generic to hold that. If we do this, that works fine for the banana, but let's add a strawberry. And suddenly it tells us, no, we can't do that because we can't convert a strawberry to a banana. In other words, there's no cast that can actually make a banana be treated as a strawberry. Well, we know all of these are objects, so one of the things we could do is we could make this be a list of objects instead. And now it will not complain, and we can go ahead and add all of our things. So we can go ahead and add banana, strawberry, and mango. And I believe that is all the fruits that we have. And then if we wanted to loop over that collection, we could, for example, do a for each, and object obj equals or in fruits. Maybe I should name that fruit instead of obj. Just to be consistent, fruit.blend, and invoke that blend method. Well, notice that now Visual Studio complains because C# is a statically typed language, and it's telling us that object does not have a definition for blend. So we can't actually invoke this in a statically typed language. Now, in some dynamically typed languages, that what they actually do is called late binding, so they don't bother to do this check of, does this actually have a method I can invoke, until runtime. And if you go back and read Alan Kay's writings, Alan Kay was one of the creators of Smalltalk, and he talks extensively about what, in his thought process, makes an object-oriented language. He actually says late binding is one of the most important pieces. So C# didn't support late binding right out of the gate, and therefore he says that's not a truly object-oriented language. So it's heavily object-oriented, but there's a couple pieces that just aren't implemented in C#. Now, since that time, we actually have added, or not we, but the creators of C# have added the dynamic variable type. So when we declare a fruit and name it as dynamic, this means that we're not actually going to check, can we blend, do we have that method, until runtime. So this basically allows C# to behave like a traditional dynamic language. And if we were to go ahead and run this, let's see, we actually are returning from these, so rather than just doing it like that, let's do a console fruit.write, fruit.blend. So with dynamic keyword, we can actually do that. Let's go ahead and take a look at what it looks like. So if we look, now we get does it blend, yellow, mushy, gooey, red, sweetness, and orange, oddness. So those three strings all get printed out as we'd expect. We might change this to a right line instead of just right so that they're on different lines. So it's a little easier to read, but we get the idea of exactly what we would be blending together and what the output would be. So that's the dynamic keyword. Now, dynamic, like I said, actually makes us treat this as a dynamic late binding language, which sidesteps all of the benefits of a statically typed language, because now we don't know until runtime if that method actually exists. So that is not the normal way that we would do it. Instead, we would want to actually use one of the polymorphism approaches to actually handle this. So with polymorphism, and especially with these fruits, one of the things we might do is say, well, let's just declare a base class of type fruit. So let's go ahead and add a new class. We're going to call this class fruit. And because we're using it as a base class, it does have to be public. And because we want it to expose that blend method, we are going to define a public string blend. And we'll go ahead and set that with a return. Mushed fruit pulp. Okay, so now we have a class fruit and implements this blend method, and now we can go into all of our other classes and say, oh, this strawberry is actually an instance of fruit, so this strawberry inherits from the fruit class. And we can do the same thing with the banana. Say the banana is also, or is a fruit. It inherits from that fruit class. And let's go ahead and change our strawberry. The banana we did mango. Let's add a mango. Say that is also a fruit. And then back in our program, instead of making this a list of objects, we can now make it a list of fruits. And because all of the fruits have a blend method, we can now go back and make this a fruit as well. So we're going to pull out the fruit, then we're going to invoke their does it blend. And before this, I'm going to add a console.writeLine as fruits. So we would expect maybe that when we invoke the fruit.blend, because this is a banana, it will do yellow mush again. Because this is a mango, we'll get orange oddness, and because this is a strawberry, we'll get gooey red sweetness. Let's go ahead and run that program and see just what happens. And notice that what we actually get is mushed fruit pulp for the strawberry, the banana, and the mango. So let's talk about why that happens. And what's going on is actually what we call dispatch. When we invoke a method, we are dispatching a message. Remember, we talked about messages and message passing as being what methods are in C#. So we are asking the particular object that is represented by this fruit to do its blend operation. And if we look at the fruit, we've defined a blend operation, which returns the mashed fruit pulp, which is what we would expect. Now, when we go to mango, for example, we have also defined a message with the same name and the same parameters and the same return type. So these are essentially doing the same thing. And if we hover over, notice that we get a little grammar marker, we get that green warning, and it tells us mango.blend hides inherited member fruit.blend. Use the new keyword hide if hiding was intended. And if you do your potential fix here, it's going to go ahead and try to hide base member. And we could go ahead and apply that. And if we do that, it stops complaining. Is that going to fix our problem? Well, if we go back and run it, notice it does not. We're still printing mashed fruit pulp for all of these. And that is perhaps the strongest argument I can make for not blindly trusting what Visual Studio is telling you. You really need to understand how the program is working and be able to interpret what it's telling you. So what it was telling us with that message, if we take that new back out, and it should kick on here in a second, what it's telling us is that the inherited member, fruit.blend, has, or the fruit has a blend method. Mango has a blend method. It's saying these are the same symbols, so we are obscuring the one that's defined in the fruit for the mango. So if we're treating this fruit as a mango, we are going to get the result of blending a mango. But if we're treating it as a fruit, we're going to get the result of treating it as a fruit. So if we treat this as a mango, we'll get orange oddness. If we treat it as a fruit, we're going to get the mashed fruit pulp. If we go back to our program, notice that we are storing this in a variable of type fruit. So all of our fruits are going in this list. We're treating them as fruits. So this individual fruit guy is taking the shape of a fruit. So when we invoke its blend method, even though we know that's a banana or a strawberry or a mango, the program is treating them all as fruits and using that fruit method because that's the one it's dispatching the actual request to. Now, if we were to substitute the dynamic keyword here, then it would go back to using what we actually expected. And actually, let's show that. So if I change this back to fruit, and we'll do another for each. And we'll do this dynamically. So if we change this back to the dynamic keyword, we'll do that late binding. And see, when we do that dynamically, we get the yellow mush, the gooey red sweetness, and the orange oddness. So that would work, but I also want to emphasize that in a lot of ways, the dynamic keyword is kind of a cheat in a statically typed language. We're stepping around the intent of the statically typed language to treat it more like a dynamically typed language. And why is that a problem? Well, let's actually create another class, and we'll see why that's a problem. So we'll create a new class, and let's create a concrete block. So we'll create a public class concrete block, and this class represents, we'll save that. And if we go back to our program, let's create another list. And we'll go back to using a list of objects. And I'm going to initialize this with all of our fruits. So that will pull in all the fruits, add them to those lists, and then we'll also add to the objects a new concrete block. And then we will write out the contents of that. Dynamic or objects dynamically. And we will just go ahead and basically do the same thing, except instead of fruit, we're going to make this an object in objects. And down here, we'll invoke obj.blend. So if I run this again, notice that this time we get a runtime exception because we put off binding until at runtime. So we could actually build and distribute this program, and it would have this hidden bug, this hidden error, that as soon as we tried to blend that concrete block is going to crash our program. So this is why the dynamic keyword is a little bit dangerous. Used appropriately, it works perfectly fine, but it does push off that binding until runtime, which means that if there's a problem in that process, it won't be detected until runtime. This is one of the great benefits of a statically typed language, is it allows us to catch a lot of errors early on during the compile time process, so that we never push software that has at least those type-related errors. It's not going to catch all of our runtime errors, as you well know, but it will help us prevent a number of those. So I'm going to go ahead and comment that out because we don't want to do that code. And now we're going to go back to looking at our fruit. We have that blend method we've defined there, and then in each of these classes we've defined another method with the same exact signature, so the same name, the same return type, and the same parameter list. And so C# is telling us, hey, you've got two methods named blend that each mango has access to, one from the fruit, one from the mango. What we want to do is actually say, even when we treat this as fruit, we want to use this blend method. And we do that with the override keyword. We say, I want to replace the method out of the base class with this method. Now, as soon as we do that, notice that we get another error, and whoops, we're still debugging, but if we stop debugging, this is going to turn red on us, and it's going to tell us that we can't modify the blend method because it is not marked virtual, abstract, or override. So by default, we're not allowed to override methods in a base class. Let's go back to look at our base class of fruit, and it's telling us we need to use a special marker. So there are a couple special markers we can use to make this be overridable. One is virtual, and that says I have a body, an implementation right here, mashed fruit pulp, but you can override that in a derived class. So now Mango is allowed to use the override keyword to say whenever this mango, even if it's being treated as a fruit, is asked to blend itself, I want to use this name. And then we can do the same thing on our other fruits as well. So we'll go ahead and change that to an override. And then we'll change the strawberry to be an override. And make sure we save all the changes there. So now if we rerun this program, we've made no changes here, which used to show all of the fruit blending, and then of course, because this is dynamic, we know that we're binding late and we're going to use whatever the actual fruits method is. We run this again, we're going to get yellow mush, gooey red sweetness, orange oddness in both of these categories. So making that override basically says that all of those base classes, when they are overridden, we're going to drill back down and we're going to use the same method for both, and it's going to be the overridden method, the overridden version of that method. So that's how override works. Now, we could go back to that base class and notice that we overrode that method in every single one of these. We don't have to. We could actually make this, or we could make a fruit without an override, or without overriding the blend method, just with no blend method in it. So if I were to go back and do that, then it would use the mashed fruit pulp instead. But I could also set this to abstract. And if I set this to abstract, the result is we no longer need to declare a body because an abstract method has no body. It's just intended to say that there will be this method in all of the derived classes. Now the other thing it's going to complain about is that fruit.blend is abstract, but this class is not abstract. Because this method has no body, we can't invoke it. And therefore, we should not be able to create an object that is just a fruit. So we shouldn't be able to run the constructor of fruit and create a fruit object and invoke the blend, because if we do, this is going to be a problem because we no longer have a body. So we also have to make this abstract as well. Now, as soon as we do that, it stops complaining. And notice if we look at our derived fruits, the override is working fine. So declaring a class abstract like this is basically saying I'm only going to use this as a base class, and we're essentially putting together a contract saying that any class that derives from this class has to actually implement this method as an override. And if I were to go add another fruit, maybe an apple, and I said public class apple, and this is going to inherit from fruit. Notice that now apple's going to tell us we have to implement fruit.blend because it was an abstract member. So we would have to add a public string blend, and no arguments for that one, and then we have to return the actual string, which would be pulp and juice, some kind of string. Results blends the apple. A string describing the result of being blended. And this is a class representing an apple. And this needs to be an override. As soon as we make that actually an override, notice that it all stops complaining. We've implemented that abstract member. If we jump back to our program, we can now add the fruits, add new apple, and when we run that program, we're going to see the apple come out of the result of blending. Now, another thing we can do is we could actually use the var keyword. And I know in 300 you were probably told not to use var. Var just declares a variable, and notice it does not represent a type, just like the dynamic does not represent a type, but this actually uses what we call an implicit type. So it's going to, as soon as we assign it, whatever we assign as the type is what type that variable is thereafter going to be. And because we're assigning it to a fruit taken out of a list of fruits, that variable value is always going to be a fruit. So it's going to get be treated as a fruit either way. So this is really no different than writing fruit, only it's a little bit cleaner and easier to write. And if you look at the coding conventions, they say you can use var if you're going to immediately use the variable, and it's pretty obvious what type it is from the context. So in this class, you are allowed to use var, and dynamic I would allow you to use as long as you understand what it's doing and you use it sparingly, only in very appropriate circumstances. But do realize that this introduces a whole new series of runtime error possibilities that simply aren't there when you're actually statically typing your program. Okay, so now we've worked through a little bit of inheritance. And one of the other important things to understand is we can go as deep as we want with inheritance. So we could, for example, have a class for an overwrite banana. So we'll declare this as a public class, and we can override our banana. So now an overwrite banana is everything a banana is, plus it's also an overwrite banana. A class representing an overwrite banana. And this class, if we jump in and take a look at our program again, where do you hide program? To close you? Staff. We could go ahead and add an overwrite banana as well. And because we haven't defined a blend method in the overwrite banana, it's going to use the one from the class it inherits from, which is banana. Now, if banana didn't implement one, then it would go back to the base class of the banana, which would be the fruit, which if we still had a virtual one, it would use the virtual body. But since it's abstract at the moment, that would actually throw us an error and say, hey, we can't do that. So if we go ahead and run this again, we're going to see the apple and the overwrite banana and how they behave. So we get, again, the first three that we had been doing. We get the pulp and juice from the apple, and then we get this yellow mush, again, from the overwrite bananas using the same string as the write banana. Now we could also override that in the overwrite banana, public override void blend, and what we'll return in here is brown and brown muck, because this is a really overripe banana. So now if I run this, because this is an override, it's overriding the override from the banana, and we should see brown muck for our overripe bananas. And notice we have yellow mush, gooey red sweetness, orange oddness, pulp and juice, and then we have the brown muck. So we have that override working all the way down. And that's important that we understand override can override a virtual method, an abstract method, or as in the case of the overripe banana, it can override an already overridden method. So we can actually stack inheritance as many levels deep as we want to go, which actually is kind of dangerous because it becomes very hard to reason about your program if you keep adding levels and levels of ancestry. So it's actually not a great idea to do that, except for when the data you're working with really has some kind of hierarchical structure that really makes sense. Unfortunately, a lot of object-oriented designers, when these languages started coming out, just really started loving that idea of inheritance and pushing it to the limit and doing probably a lot more inheriting than really needed to be done in most cases, and that can lead to some real challenges when it comes to maintaining code. So even though we have this great power, we want to be careful about how we use it and only use it in a responsible and maintainable fashion. So that's inheritance. Now there is another polymorphic mechanism for working with objects in C#, as well as some other languages like Java. And this is a weaker inheritance mechanism, so a weaker mechanism than inheritance. So we often call inheritance a strong is-a relationship, because we're saying an overripe banana is a banana. It has everything that is a banana plus the attributes of being overripe, just like it is a fruit. It has all of the aspects of being a fruit plus all the aspects of being a banana. So that's a strong is-a relationship. The other kind of relationship we can declare is called an interface. So we can do this, go ahead and add a new item to our project, and we can actually find interfaces declared there. And we're going to declare an interface iBlendable. And it is a convention that you would put an I in front of any interface just to indicate that it's not a class, but it's actually an interface. So we'll go ahead and declare that. And we'll want to make this public. Now, an interface looks a lot like an abstract class. For example, we would declare method signatures that don't have a body, that anything that implements the iBlendable would have. So in this case, a string and then blend. But there are a couple important differences. One is, notice that we didn't declare this as public or private. And in fact, if we put public in front of it, it's going to complain at us and say public is not valid for items in C# version 7.3. Please update to language version 8.0 or greater. The reason it's not acceptable is every method we declare in an interface is automatically public. So up to version 8 of C#, they didn't even bother to put modifiers in. It was just understood that that was going to be a public method. So we go ahead and put it in the method signature, so the return the name of the method plus the parameter list, in this case an empty list, and then we end it with a semicolon. No bodies in an interface. And we can have as many methods we want to declare in here as well. And this is an interface for things that can blend. And we comment our method. Returns the result of blending the object. And in our return statement, a string describing the results of blending. Okay, so that's really all we have to do for an interface. We can have as many methods as we want. And then we can go in and we can, for example, on our cell phone, say that this is going to implement iBlendable. Now we're saying the cell phone is going to implement that blend method. We're going to get jagged chunks of plastic, glass, and electronics. Don't actually blend a cell phone in real life, because a lot of the things that are coming out of that are actually some pretty toxic chemicals, and you really don't want that on the blender that you're using to make your shakes and malts and whatnot. Okay, So that's a cell phone. We could also do the ice cubes. We can say that's an iBlendable. And because it already has that method, it's going to be happy with that. Now, if it didn't have the method, so if I just took that method out momentarily, we're going to see this get underlined and say you have to implement that member iBlendable.blend. So the way to think about both an abstract class and an interface is a contract that you are saying anything that implements this interface or anything that implements the fruit base class is going to implement the methods that we've specified. So that's really what those two things do. But again, with a base class, we can actually have public and private methods that are intended to be overridden abstract methods. We can also have non-abstract methods in an abstract base class. So we could, for example, public string, actually public int age get set. So we've just declared a get method and a set method for an integer describing the age of a apple and or any fruit. Age of the fruit. The fruit, not Groot. And maybe we're going to put in the value and say that this is measured in days. So we're keeping track of the age of the fruit. Maybe this is part of a program for managing inventory in a store. And once it gets to a certain age, we really don't want that to be on the shelves anymore because it's going to be starting to maybe not taste as good or something along those lines. That also means that when we're treating this as a fruit, we can console.write line fruit.age. And that's going to print out the age of our fruit. And maybe I'll go ahead and put this in a template string so I can wrap it in parentheses and make that appear right after what we're blending, just for the fun of it, and so we can see that that method is going to be called for all of those fruits. So again, one of the core ideas about inheritance is that we get everything that's defined in the base class, and we don't have to necessarily override it. So in this case, we will get that property that had a getter and a setter and would give us an age. Now we didn't give it a default value, so it should be 0 for all of these. And you'll notice they're all marked with zeros, so that's exactly what we'd expect. And the point of that is if we go back to the iBlendable and we tried to do that public int age, notice that it tells us public, actually we can do this and it's not going to complain, but there's a very important difference here. Here, this is the signature. This does not create a private backing variable, where here this is actually the declaration, and we're using that syntax, which actually does give us that value. So maybe a different way of thinking about it is, instead of doing this, let's do this as a field, and we'll explicitly give it a value of 5. And if we go back to the iBlendable, and if we tried to make this a field, it's going to tell us, no, you can't do that, because we can't declare fields in an interface, because an interface doesn't actually declare any state. An interface is only behavior, only methods, which is why we could declare a property, because a property is actually consisting of potentially a get method and a set method, either one or both of those, but it's actually just methods. Kind of clouded things a little bit because we also looked at how we could tweak or use the auto implementation syntax to get the compiler to actually create the state for us. But yeah, in an interface we can only declare methods and properties that need to be implemented in whatever class actually implements the interface. Another thing to notice is that we are not overriding that method. We are simply implementing that method, so we don't need an override. In fact, if we put an override, it would actually complain because there's nothing for us to override. Notice right there it says there is no suitable method found to override. So overriding is strictly an inheritance mechanism. It doesn't apply for interfaces. Now, what's the benefit of this approach using an interface? Well, we can create a list of disparate objects. So if we come back to this idea of list, and we could actually say an iBlendable. Blendables equals new list iBlendable. And let's go ahead and initialize this with our fruits list just like we did previously. Now notice it's going to underline this in red because our fruit does not implement that interface, but we could go ahead and say it does implement that interface and it will immediately stop complaining. And if we go back to the program, it's going to stop complaining there. And we know because fruit has required that everybody that is derived from it implement this blend method, that meets that requirement. So here, an apple automatically also gets the iBlendable interface from that base class. But we can also explicitly state that the apple implements that interface. Now, we can do as many interfaces as we want. So I could also do an iClonable, for example, which would say I've implemented a clone method, which I haven't. Noticed it's telling us we need to implement the iClonable.clone method. But we can list as many interfaces as we want. We can only have one base class per class, though. And the mechanism is the base class always comes first, and then we do a comma-separated list of any additional interfaces it implements. So let's go ahead and leave it at that. Now that we've made the fruit an iBlendable, and even though an overripe banana we don't have as an iBlendable, it gets it because of that fruit. So now if we go back to our program, notice it's not complaining, and even though we're pulling in this list of fruits, which is strawberry, mango, apple, and overripe banana. And we can add to that any other iBlendable. So we can do blendables.add and throw in a new cell phone. What a waste of a cell phone, right? Brand new cell phone. Blendables.add, and we'll do new ice cubes. And then we'll go ahead and do the same kind of writing things out, but we're going to do iBlendables. And we'll go ahead and change this to a var blendable, or we could make it an iBlendable. In either case, it's going to be treated as an iBlendable because that was the type of the templated list. And this is going to be blendables, a list of blendables, and then we need blendable. And now if we invoke this, we should see all of the fruit being printed first, followed by our cell phone, followed by our ice cubes, and we'll go ahead and run that. And notice when we get down to the iBlendables, we get yellow mush, gooey red sweetness, orange oddness, pulp and juice, brown muck, jagged chunks of plastic, glass, and electronics, and little chips of frozen water. So it blends all of those. We can use those all in a very statically typed way and actually represent our list as a list of iBlendables, even though the cell phone is not a fruit and has nothing to do with fruit, and the ice cubes are not fruit and really have nothing to do with fruit. So sometimes you might wonder, should I use inheritance or should I use interfaces? And the answer really depends on what your classes are doing. If they have a shared relationship, if there's data that really makes sense to be shared amongst both classes, then you might want a base class. On the other hand, if they really have very little to do with each other, like a cell phone and a fruit are very different things, we normally wouldn't categorize them together in any way other than maybe one like this where we could say, well, we could throw them both in a blender, surely. Then it really makes a lot more sense to use an interface. So they get us kind of to the same place, but they offer different benefits depending on which one you're going to end up using. And it really becomes down to a decision based on the nature of the program that you're writing. Now there's one more thing we should probably talk about with inheritance, and that is sealed. So the sealed keyword we can use in conjunction with override. And for example, if we declare this method sealed, what that means is that this can no longer be overridden any farther. Public sealed override string, just override. There we go. So if we make this a sealed method, what we're saying is I don't want this to be overridden after this point. And if we jump to our overwrite banana now, notice that it's now telling us we cannot override inherited member banana.blend because it's sealed. So this says no more overriding. You're not allowed to override any further down the chain. So that's what the sealed keyword does for methods. We can also put the sealed method on a class, or a sealed keyword on a class. And what that says is the entire class is no longer allowed to be overridden. And if we come in here and notice that it says, oh, banana cannot be overridden because we've actually declared it as sealed. So sealed is really, in a lot of ways, a technique for protecting our classes that we've written from being overridden by somebody else, and then they potentially modifying the internals of our class by using override methods to change the behavior. So we usually see sealed used with library classes in an attempt to basically keep programmers from altering how those library classes work. For example, the list that we're using in program here, this list class, is actually I'm not sure if this one's sealed, but a lot of the collections, a lot of the base libraries are actually going to be sealed classes, especially things like math. The math class is a sealed class because they don't want us modifying the behavior of existing methods in the math class. So that's a way of kind of protecting us from programmers maybe inserting some unusual behavior to replace poor behavior, and then that can cause all kinds of problems for other programmers down the road because we know the expected behavior, but some clever programmers decided they didn't like that default behavior. They wanted to behave slightly differently, and we're still writing code expecting it to work the old way. So that's what the sealed keyword is and where it comes in. All right. That wraps up our discussion of polymorphism in terms of object orientation, and especially in what we call dynamic dispatch, deciding which version of a method we're going to actually invoke if we have more than one method defined. So if we have a polymorphic method, either because of inheritance or because of the use of interfaces, that gets us where we need to be. So it's been good talking to you. I hope you have a wonderful day. Stay healthy, and we'll see you soon.